Hey guys, welcome to Unit 2, Periodic Table and Trends, Section 1, Periodic Properties and Trends. This is a video for Gen Chem, so if you're in Honors Chem, close out, go to the other video that's labeled Honors. Otherwise, let's go. Quick review, periodic table is organized by atomic number as you move left to right. All the vertical columns are called groups or families, the horizontal rows are called periods, and we develop trends as the periodic table is designed. The first concept that we're going to look at is reactivity. It's a trend, but it's a minor trend. And reactivity basically just refers to how likely something is going to be to react with other things. If something is very reactive, it reacts with lots of different things. If it's not very reactive, it does not react with very many. It may only react with a few or none at all. There's two different trends here, one for metals, one for nonmetals. So looking at a periodic table, for metals, as you move down a group, or left across a period, so basically as I'm moving down and left, so essentially diagonal across the period, metals are becoming more and more reactive. And that makes sense because definitely as we move left across the period, because as you move left, over on the left-hand side is where we find our metals that form +1 and +2 ions. That means that they are only 1 or 2 electrons away from having their full outer valence shell. They want to lose their 1 or their 2 so that they can get to that. That means they're really close to their goal, so they really want to get there. So the more close you are to your goal means that you are more likely to be reactive. So by that understanding, the most reactive metal is francium. That's in the far bottom left corner. For nonmetals, the trend is the opposite, and that probably isn't magnificently surprising because nonmetals are on the on the right-hand side of the periodic table. They have charges like -1 and -2. That means they also are very close to having their goal. They are close to being at the 8 valence electrons that they want. So as you move to the right and up a group, or to the right across a period, you're going to find the most reactive nonmetals in the top right, that being fluorine. For those of you that are visual folks, here you go. So metal reactivity increases as you move left and down. Non-metal reactivity increases as you move right and up. So we find fluorine being the most reactive nonmetal and francium being the most reactive metal. Okay, so first thing, I want to make sure that as we go through the trends, there's only a few of them, but I want to make sure you keep your notes organized. And I want to make sure that you label them in a very specific way, all right? So make sure that when you write the name of each trend, highlight it or make it stand out with stars or whatever. But this one in particular, this first one and the second one we're going to have, make sure that you put stars next to these, okay? These are what I call the parent trends. Okay, write that on your paper. You're going to need it. Parent trends. The parent trends basically means these are the trends that every other trend is based off of. So let's talk about the first one. The first one is nuclear charge. Nuclear charge is referring to how charged the nucleus is. We know that when we have an atom, we have our nucleus at the center. That's where all of our protons and neutrons are. And then we have our electrons out on the rings. Okay, the electrons are negatively charged. The nucleus is made up of positives and neutrals, which means the nucleus is positive. Okay, as a whole, the nucleus has a positive charge. The electrons have a negative charge. So what you're going to see is that the electrons are attracted to the nucleus. The more positive the nucleus is, the more the electrons are attracted to it. So as I move right across a period, I'm increasing my atomic number. Atomic number. That means that I have more protons, a stronger nuclear charge. So the more protons I have, the stronger the positive charge in the nucleus, the more the nucleus is going to pull on the electrons. Now that's going to mean a lot because that means that they're holding onto them very strong. That means that the nucleus is holding onto the valence electrons and pulling them very close. So both of those are going to be extremely important as we move through the rest of the trends. This trend, I also want you to put asterisks beside and underline because this is also one of the parent trends, okay? This is one of the trends that really explains all the other trends. And this trend is shielding. Shielding is referring to how many energy levels a atom has. We know that the further down on the periodic table, the more energy levels things have. So that's shown right here. As you move down the periodic table, you have more and more energy levels. And the reason that shielding is important is because the energy levels act like walls, essentially, and they block the nuclear charge. Now, how that works is that we have our nucleus, which is positively charged, and if I have electrons at the first energy level, n equals 1, those electrons are pretty close to the nucleus, and the nucleus can hold on to them pretty well. But as I keep adding energy levels, it's getting messy, whatever. If I have electrons out, let's do it over here. If I have electrons that are way out here, every one of those energy levels that's in between that electron and the nucleus is going to cancel out some of the charge of the nucleus, because that's just what it does. It makes it further and further away. So this valence electron out here is going to be further and further away from the nucleus. The valence electrons are further away from the nucleus, the more energy levels there are. So there's less pull from the nucleus on those electrons. So that means less pull, the more shielding there is. That also means that those electrons could easily be lost because there's not much of a pull from the nucleus on those outermost electrons. Okay? So again, the two parent trends are nuclear charge and shielding. Write that down. Okay, so starting at a nucleus, which is positively charged, we have our energy levels around it, and you guys do know, don't correct me please, that these are not perfect. I'm aware of that. We know that in quantum mechanical theory that they're not rings. This is a Bohr model. Just go with it. All right, so the nucleus has pull on the outermost electrons, okay? That pulls in on the atom. Okay, so atomic radius is essentially the radius of an atom. If we have a circle and it has a center point, then the radius is half of the diameter. So radius is half of the diameter of the atom. So the stronger the nuclear charge, the more protons I have in the nucleus, the more it's going to pull in on those outermost electrons. So if I have a very positive nucleus, meaning a very high atomic number, a very high atomic number and a very high nuclear charge means it's going to pull in on its outermost electrons more stronger. It's really going to pull in on the electrons on the outer sides. So that means that if I move right across the periodic table, that's a bad color, but you get the idea. If I move right across the periodic table, meaning I'm adding protons, it's going to pull more and more in on those outermost electrons. So as I move right across the period, the atomic radius decreases because the nucleus is pulling in so hard on those outermost electrons that it's going to shrink the radius of the atom as I move across and add protons. As I move down a group, shielding comes into effect, okay? Because if I just have the nucleus with its positive charge and one energy level, those electrons are going to be pulled in pretty well. They're going to be pulled in pretty tight. But if I have a bunch of energy levels, sorry, now it's messy. If I have a bunch of energy levels, it's going to, the nucleus has less of an effect because every energy level, the nuclear charge is canceled slightly. So the more shielding there is, the more atomic radius is going to be larger because as I move down a group, I'm going to have a larger atomic radius. Here's the basic trend. As I move right across a period, nuclear charge increases, so I have smaller atomic radii. As I move down a group, shielding is now blocking the nuclear charge more and more every period I move down, so that means the nuclear charge can't pull in the outermost electrons as easily. Ionization energy is the next trend. Let's break that word down a little bit. Ionization, okay, means to become an ion, okay? And energy, of course, is just the energy that's required to do that, okay? So by definition, it's the energy required to remove an electron from a neutral atom, meaning the energy required to form a cation. Okay, we know that metals are more often likely to form cations than nonmetals because they're on the left-hand side of the periodic table. So listen to this. Cations, or to form a cation, the ionization energy is the energy required to form a cation. So if something is very willing to form a cation, meaning it's something that easily forms a +1 or a +2 charge naturally, the ionization energy is going to be really low because it's not going to be really difficult to tell sodium, hey, you normally form a +1 ion. Form a +1 ion. And sodium's like, cool, I can do that. That's easy. So it doesn't take a lot of energy to do that because those elements on the left-hand side of the periodic table have very low valence electrons. They want to get rid of their valence electrons, so it's very easy to convince them to do that. Those on the right side of the periodic table that are traditionally used to forming anions, or things that are used to forming -1 or -2 charges, it's going to be really freaking difficult to convince it, hey, I know you want to gain electrons and form a -2 charge, but why don't you just get rid of one? No. Okay? That's like telling someone, I know you're hungry and here's some food, but why don't you just not eat and just give everyone else food? That's weird. Okay? That doesn't make any sense, nor would it make any sense for an anion to easily give up an electron, or a compound, or excuse me, an element that forms anions to agree to easily give up an electron. So ionization energy is going to increase as I move across a period from left to right, and it has to do with the proton, or excuse me, the nuclear charge as well. Just like with atomic radius, the increase is caused by a more positive nucleus holding on stronger to those outermost electrons. So as I move right across a period, the nuclear charge increases. That means that I'm going to hold on stronger to my outermost electrons, which means it's going to be way more difficult. I'm going to require a ton more energy to actually get that atom to release an electron, which is what ionization is referring to. So very high ionization energy means it's very difficult to remove the electron. Here's the trend for ionization energy. So you find that the elements that it's going to be the most difficult to remove an electron from are going to be those up in the top right corner. Boom, group 18, that one should stand out because, yeah, it's going to be difficult to get an atom to agree to get rid of electrons if it already has the 8 that it wants, okay? If an atom already has 8 valence electrons, it's happy. It does not want to lose an electron. So the energy is going to be extremely high for any atom on that side of the periodic table that is trying to be convinced to get rid of an electron. Last trend is electronegativity. So we said ionization energy is how much energy it takes for an atom to form a cation. Electronegativity is how likely an atom is to form an anion, meaning a negatively charged ion. So essentially that's saying, how much does this atom actually want more electrons? Well, it shouldn't surprise you that those atoms that form -1 and -2 charges, and of course -3 and -4 as well, are going to have really high electronegativities. Electronegativity is essentially the ability of an atom to attract electrons from other atoms. So if I have 7 valence electrons and I want 8, it is going to be really, really likely that I'm going to try to gain that 1 electron to have 8 valence electrons. So as you move right across the periodic table, due to that increase in nuclear charge again, I am going to increase my electronegativity. Those atoms on the right side of the periodic table have very high nuclear charges, which means they really, really, really want to get to that 8 valence electrons. The closer I am to 8 valence electrons, the more interested I am in getting to 8 valence electrons. So if I have 6, 7 valence electrons, I really want that last one. So again, here's the trend for electronegativity. You'll notice that the highest electronegativity is fluorine over here. The noble gases on the far right of the periodic table, group 18, are showing no electronegativities. So they have electronegativities of 0. That's weird. The reason for that is because electronegativity is how likely that atom is to want more electrons. They already have 8 valence electrons. They want nothing to do with any more electrons. So they have zero interest in electrons. So electronegativity is really what interest does that atom have in more electrons. Over on the left-hand side of the periodic table, things like lithium and sodium, they're trying to get rid of the electrons they have. Why would they want more? On the far right, they're trying to get to that 8. They want that extra electron. They do want those electrons. But group 18, they already have 8. They don't want electrons, and it's going to take a heck of a lot to convince them to get rid of the ones they have. All right, so if you've watched the video this long, then you will know that you're going to have a quiz, 3-question quiz, on this section of notes in class next time. Okay? It's going to cover just the basics, nothing intense. So review your notes, write yourself a little summary to summarize them, and prepare yourself for a short little quiz. Have a great day.